So, welcome to this session. In this session, we'll focus on symmetrical fault analysis and the deriving point errors. When we say a symmetrical fault analysis, the situations that occur in a power system will affect equally all three phases. And in addition, when we talk of about the deriving point, is a concept where we can calculate the equivalent impedance that will be observed by a source when the system is subject to a fault. In a power system, we classified the bus system into three: slack bus, PV bus, as well as PQ bus, based on their role in a power system. So you can remember what we for try to say for slack bus. Like for slack bus, we have fixed voltage and the voltage angle, whereas the power, both active and reactive, will be calculated based on the power mismatch. But when it comes to PV bus, active power and voltage will be fixed, but voltage angle and reactive power will be calculated based on the power mismatch. Whereas for a PQ bus, the power, both active and reactive, will be fixed, but voltage and the voltage angle will be calculated using the iteration method. Considering 100 MV as base power and 11 kV as base voltage, we'll see how to calculate the symmetrical fault analysis. That's the circuit breaker required, both the speed and interrupting capacity. So to go to that, first we'll consider the deriving point impedance. This deriving point impedance is a very straightforward and can be obtained from a Y-bus matrix. So you remember that a Y-bus matrix is obtained by using uh, diagonal and off diagonal. When we say off diagonal, it's part of a Y-bus matrix which is not diagonal. But when we say off diagonal, it's a point which is contribute to the impedance point or driving point impedance. So to get the Y bus through the driving point impedance, we'll use a diagonal matrix as the inverse of diagonal matrix is taken as driving point impedance. For example, we have three bus. Bus 1, we have a diagonal matrix component of Y bus matrix 8.33, which is obtained as the summation of admittance connected to that bus. First bus, for example, 8.3. And if we take the inverse of that, it will get a deriving point impedance at bus 1. Again, for bus 2, so, like that, the same scenario is used. So for n bus, we can get a deriving point impedance using this concept. So when we calculate the voltage, current, and interrupt the capacity of a circuit breaker required for the fault that occur at any bus, we can calculate the magnitude of a current considering the pre-voltage magnitude and uh, driving point impedance. So the general formula to calculate the driving point impedance as well as the magnitude of a current under a faulty condition is often using this equation. I fault is equal to pre-fault magnitude of voltage at a place where a fault occurred divided by the deriving point impedance at that place. So we can use this equation. Pre-fault magnitude of a voltage multiplied by the Y-bus matrix, diagonal Y-bus matrix at that point. So this is the definition for those variables. V pre is means the magnitude of a bus K voltage before a fault, whereas ZKK is 1 over the Y bus diagonal matrix at bus K, and we can take ZKK as 1 over YKK. So the diagonal matrix is very important to calculate that. But we have to consider this system is used for a 3-bus fault. Again, if ZF is there, we could consider the ZF into consideration when we are calculating a fault current. So the general equation will be obtained as pre-fault voltage divided by ZKK plus fault impedance when we have a fault impedance magnitude. So the general procedure is like stated here in this 5 step. First, we will build a Y bus. Then we will make calculation considering a deriving point, and we calculate a magnitude of fault as a bus. Then we can compute a Thevenin equivalent impedance, which is 1 over YKK. If a fault current is required, we can calculate fault current using pre-fault voltage as a place plus driving point impedance. Post voltage at a faulted bus is 0. At that time, we have 0 magnitude of Vk. But if we have ZF, we can calculate IF times Z will be the magnitude of the voltage at a faulted bus. So this is the key points we have to consider when we are calculating a three-phase voltage. Only positive sequence network will be used, since it's similar for all phases. All three currents are equal in magnitude. Fault depend upon a network string seen from a faulted bus. So that's why the ZKK, or what we call a driving point impedance, is very important in calculating the magnitude of a fault. For example, consider those previous examples. We have three bus, we have three diagonal Y bus matrix. So if a fault occurs, we can calculate the magnitude of a current at each bus. For example, for if bus 1 is like bus 1, pre-fault magnitude of voltage is 1 per unit, whereas the driving point admittance is -3. So we can calculate the driving point impedance by taking the inverse of this. It becomes like this. Then current can be calculated by dividing voltage by Z impedance, since ZF is equal to 0. So we obtain this magnitude of a current at per unit. Since minus J is minus 90, we can take 8.33 as 90 degree. Again, if the fault occur at bus 2, pre-fault voltage magnitude is 1, and we have a deriving point impedance of this. So the magnitude of voltage at bus 3 is this. So we can see that. You can see that the fault magnitude is high at bus 2. Again, for a bus 3, we can use the same. And in addition to that, the magnitude, the approximate faulted MV at bus 1 is calculated by using root 3 times VLL, considering 11 kV. For example, in our case, IF is also already calculated from this relation. So we can use this as magnitude of a fault that occur, magnitude of a fault that, or the power that run in that faulted bus. In addition to that, weak fault bus also the same. So interpretation. So a very high fault current occur at slack bus. Bus 1 is strongly connected to entire system, whereas bus 2 is connected to bus 1 and the bus 3, and all three bus current are equal in the 100 degrees phase difference. Again, when you come to bus 3, same scenario is repeated. We use pre-fault current, then driving point impedance is there. We can calculate IF, then this. So if we consider this, those three buses, bus 1, bus 2, bus 3, we have these bus representations like PV bus and the PQ bus. ZK is obtained like this, IF is obtained like this, and the angle is -90, and fault magnitude in MVA is like this. So the fault magnitude as bus 2 is high. If we use a base of power of 100, we can calculate the actual current, and actual power requires actual current at bus 2 is 4,720 ampere. So we can select the circuit breaker based on this. The circuit breaker should withstand this, and we have to select the MVA of the circuit breaker as well as the tripping speed. So